Okay, moving on to another sensor. We also have in the urban board what we call an indoor air quality sensor that measures what we call equivalent total volatile organic compounds. So volatile organic compounds is any compound that comes from organic sources that has some sort of volatility and can be diluted in air. The total amount means that we are not the T in the ETVOC stands for something that we are not distinguishing or being very specific about the type of volatile organic compound that we are using. And the equivalent means that we are basically not only measuring volatile organic compounds, but also other toxins and chemicals. And this can come from a wide range of things, some of them from paints, varnishes, cosmetics, many cooking, and many other aspects. And the sensor in general, we have it in the board because, of course, we like to experiment things, but we do not think that the sensor provides accurate readings or readings that should be used for high-end scientific studies. For these, there are other sensors that are more specific and have more repeatable readings, but it could be used as an indication of indoor air quality levels to some extent, and with careful analysis of the data. It also gives a metric called ECO2, and there E stands for equivalent, and is very important because it's not CO2 at all. What we are measuring is a derived metric that comes from the total volatile organic compounds, and that is the equivalent CO2 or the amount of CO2 that we would have from those volatile organic compounds that cause the same global warming potential. So the term ECO2, just to be very clear, is not CO2 at all, but is a derived metric calculated from the other readings, so volatile organic compounds in this case, and that is equivalent in terms of how much those toxins and those chemicals warm up the planet in terms as if we calculated that in CO2 equivalent. Having said that, of course, we also support CO2 with other types of sensors, but just so everything is clear, there's no CO2 actual carbon dioxide reading in this sensor in particular. And also, we are, well, first of all, the sensor is going to be discontinued or has already been discontinued, and we cannot manufacture it with this sensor anymore, and we will replace it with another potential indoor air quality sensor as well for future versions of the device. This is basically what I was explaining earlier, and just to mention that these air quality measurements, we call them as indicative, and they are affected by many things. Some of those things are temperature and humidity, also ozone. So mostly in outdoor environments, it will be affected by ozone as well, and it reacts to many things. So it should be considered as an indicator and not as a specific particular sensor. Also, the sensor is of the type of what we call metal oxide sensors. So these sensors are well known in the low-cost world and are used in many applications, most of them safety and not so much in environmental monitoring, although there's an increasing trend on the usage of this, and a lot of people are studying them to see how they can calibrate them. And but they are not meant for fine pollution monitoring. So it is able to obtain trends and provide air quality indicators, but it shouldn't be used as of the current state of the art as a fine pollution monitoring. And this question is probably too direct, but we don't think that they can be calibrated reliably for long term, and other type of technology should be used in case that you want to measure these particular pollutants. Moving on to another sensor, so ambient light, we have a directional ambient light sensor, meaning that it's able to measure both visible and infrared light sources, but basically in a beam. So wherever you are pointing the sensor to, you will be measuring that amount of light. It's not a diffused sensor that can measure all the light around it, but is a directional one. So if you're pointing it to something white or to something black, it will give you different readings. And it will also capture both visible and infrared sources. It is already calibrated. It doesn't have any drift, but important that it is a directional sensor. And in the future versions of the kit, we are looking into providing more logical, probably light sensor that also captures, or that captures better diffused light, and that is not so directional. But this is what we have at the moment in this device. Finally, probably the most interesting one of the sensors, probably be more than the noise, is the particulate matter sensor, which is the one that we use for proxy for air quality and air pollution, of course. So what we're measuring here is the amount of solids, microscopic solids with different sizes. Of course, we all know that we can breathe and inhale all these particulates, and that can go deeply into our lungs and provoke different types of pathologies. Some of them can also go into the bloodstream. And we have to say that measuring particulates is very, very complex. And low-cost sensor technology is based on a principle that I will talk about it in a second, that of course has its limitations, and as every low-cost sensor, it is of course not perfect. So the sensor in question that we use is called the Plant Tower PMS 5003, and it's a type of sensor that is called light scattering. We have one sensor connected to the urban board, and is of course this silver box with a fan and a laser inside, that has these performance characteristics and that can provide different sizes. So it can measure PM1, PM2.5, and PM10. And it can also not only give you the mass, but also the count of the different sizes. And those bins, the categories of the sizes that it can give, is from 0.3 to 0.5, and so on and so forth, up to 10 micrometers, with quite a decent accuracy for the cost. Calibration and drift is something that we will check, or I would elaborate a little bit further on the following slides. So first, let's see what we're measuring. So we're measuring particles that are smaller, or of the range of the size of human hair. So human hair roughly is 50 microns, and we are going down to 10, and even farther down. The way that the sensor works is basically putting airflow in front of a laser that reflects on the particles, and that gets, let's say, diffracted or reflected onto a photodiode. Basically, this is the same as a camera, but very small and not so accurate. And basically, we capture how many particles are passing in front of the laser by counting how many shadows we are projecting onto this sensor. So as you can see, there is no chemical analysis on this. And of course, there's a lot of assumptions that we're doing. Some of them is that all the particles have the same shape. So we cannot analyze the type of shape that we have. We consider them as spheres. And as you know, particles can be of many different shapes, especially when we are talking about combustion. related particles that can have very different elongated or more spherical shapes due to the presence of many other compounds. We don't know anything about the color of the particles, so we are basically assuming that all of them have an average, what is called reflectivity index. Of course, white or black or yellow or whatever color particles will have different ways of reflecting the laser. And this means that we don't know anything, we don't have any color sensor that is able to tell us what color each particle is. And finally, we don't know anything about the composition. So we don't know anything about the density. And what the sensor does basically is, since it's counting particles that are passing in front of it, it's assuming all these things and then it's giving us a number of particulate matter in terms of mass per volume. So of course, there's a lot of assumptions that are not always going to match. And the manufacturer assumes certain things as, in particular, all of these. And of course, not all air is the same, and not all the particles that are in the air are coming from the same source. So they could come from dust, pollen, combustion sources, and so on and so forth. But of course, they are not always the same. And in different parts of the world, of course, they will be different. One important thing, and this is probably one of the most frequently asked questions about the sensor itself, is what happens with the different sizes. So a lot of people will ask what happens with the PM10 readings, and why are they so similar to the PM2.5 and the PM1 readings. So for understanding that, we have to understand a little bit what is the concept of particle size distribution and how the sensor performs in each of the particle sizes. So to understand this, we first talk about the fact that the different particles in the air, of course, have different sizes, and that we are trying to evaluate and count each of the sizes in with one single sensor. Professional or more advanced sensors are able to perform very well by counting those particles at all the different sizes. So in this graph, we see at the moment very commonly used type of particulate counter or particle counter, sorry, called GRIM, that you can see that has a very good detection efficiency on all of the different sizes. So on the horizontal axis, we have the particle size, and on the vertical axis, we have the efficiency. And we see that it performs very well on all the cases. And no matter the size of the particle, we will get an efficiency of roughly 70 to 80%. Other sensors, in particular the low-cost sensors, will not show such a good efficiency. The sensor in question is the one that we have on the left. So we see that the efficiency of the blue, red, and yellow traces are good, all of them on the low end. So we are able to detect particles that are very small. But as soon as we go further into the right or the horizontal axis to the right, we see that we are not counting particles at all, and that we have almost zero efficiency on them. And that basically readings of PM1 and PM2.5 are very similar, and PM10 is a little bit more different, but still it doesn't go as far as it should go on the right side of the axis. Other sensors show a better performance, but for instance, the red should be a little bit more widespread onto the right as well. But obviously, this is not the case, and as we can see in the graph, and it doesn't resemble at all to this other graph that was in the more advanced instrument. So what happens when we are using this sensor for evaluating particle particulate matter. So as a first example, imagine that we have a volume of air that has a distribution of particle sizes that are mostly on the left side. So is heavily skewed to smaller sizes. Then since we have very good counting efficiency on that area, we will have very good accuracy. However, if we have a distribution that is coming or mostly skewed on the right side, we will have very low efficiency on that end, and we will be missing basically all of the particles. But what happens if we are on the center? So what happens if we are on the on a middle or a distribution that is equally distributed on both? So basically, we have an okay, we could say, efficiency, because we will be missing some particles and capturing others very well. And this last example, of course, is the general case. So we don't know what distribution we have in general, and unless that we know that we are always measuring on the low end, the sensor cannot be used, of course, as a fine instrument, especially on the higher end. However, a lot of studies have proved that the sensor can be used as an indicator, and it will depend on the area, the geographical area, and other sources that can be of information for us to know what is the actual particle size distribution, and then assess whether or not this is a good sensor or not. Another topic here is that what happens with the larger particles in general, and is this something that we can just simply replace this type of sensor, or that and we say that the plant tower PMS is a bad sensor because of that? Well, it is not the case that the plant tower is a bad sensor and that is a bad choice. Is the type of technology that we are using, because if we want to measure large particles, we have to go to the right side of the spectrum, and the probability that there are big particles on a certain amount of volume that we are sampling, which is very small, it is very low. So there are more in general, there are more small particles in a certain volume than there are larger particles. So since our volume, we cannot sample an infinite amount of air, we are limited to the amount of sampling that we can do with one particular sensor. Then normally what manufacturers do for measuring large particles in these type of sensors is that they estimate based on the readings of PM1 and PM2.5. And as we all know, estimations sometimes can go wrong and sometimes can go very well. And that depends on the algorithms implemented inside of the sensors, but that are basically relying on statistical assumptions of what are normal air quality profiles and particle size distributions in different types of scenarios. For instance, urban scenarios or wood burning scenarios or others. So even if the technology or if this particular sensor doesn't perform as well, it is not the case that we're going to be able to simply just replace this sensor by another one, and that we will be able to measure particles well, but that we will have to live with that in general and go to another type of technology, spending way more money to be able to measure this in accurate terms. And of course, try to improve little by little the way that we process the data and understand how the sensors are working. But it won't be the case that we can just buy another sensor and get very good readings, as the technology doesn't allow for it at this moment.